Let's focus on loop 1. So in focusing on loop 1, we only have to pay attention to current 1. We don't have to pay attention to the current that goes through resistor 2, nor do we have to pay attention to loop 3. So in evaluating loop 1, we have to be aware of the two currents and how those two currents are kind of opposite in direction as we approach node C. So in applying Kirchoff's loop rule for a complete loop, we have to say that the sum of the potential differences for a complete loop is equal to 0. So for us, let's start and end at point A. So the voltage from A to B plus the voltage from B to C plus the voltage from C to D plus the voltage from D back to A has to sum to 0. So let's look at each of these voltages in turn. The voltage from A to B is the voltage that goes across battery 1. And we said that voltage that goes across battery 1 is equal to psi. And let's go ahead and put the voltage that is part of battery 2 is equal to 2 times the voltage of battery 1. Now our original circuit, the resistor that's attached to battery 2 has the same resistance as battery 1. And the resistance of battery 1 we had identified to be 2 ohms, which we are calling 2R. So I'm going to label that in our diagram as 2R, which is twice the resistance of resistor 2, which we will label as R. Okay, so the potential difference from A to B is just the potential that goes across battery 1, which is psi. And it's going to be a positive EMF. And the reason why it's positive is because we are going across the battery 1 from the negative terminal of battery 1 to the positive terminal of battery 1. Whenever we do that, we add the EMF of the battery. And that's because, remember, when we go from the negative terminal of a battery to a positive terminal of the battery, when we evaluate voltage, when we move along a path, we add the EMF. So now let's look at the voltage from B to C. The voltage from B to C goes across resistor 1. So in doing this, let's look at resistor 1. Here is resistor 1 from B to C. Let's indicate our path. Notice our path is going from point B to C, so I'll indicate our path to the right. And let's indicate the direction of the assumed current. The direction of the assumed current is to the right as well. So whenever your path of analysis is in the same direction as your current, that resistor has a potential drop. In other words, the potential difference from one end to the other lowers. And so that potential difference from B to C is equal to minus the product of the current and the resistance. So that potential difference from B to C being equal to minus current 1 and the resistance of resistor 1, which is equal to 2R. So I'll rewrite that as minus 2I1R. So the main thing to note on this one is how the direction we evaluated voltage from B to C is in the same direction as the assumed current I1. Whenever that happens, that resistor consumes voltage. The voltage, the potential difference from one end to the other end will reduce. Now let's look at the segment from C to D. So the voltage from C to D. Well, in looking from C to D, notice how we go across another resistor. Now this resistor has the same resistance as the resistor that's attached to battery 1. So it is R1. And we said R1 is equal to 2R. And in going from point C to point D, notice how the current I2 is opposite to the direction in which we are traveling the loop. So we are traveling from C to D, but the current is opposite that, from D to C. What that means is that the resistor will have a potential gain in resistance. And so the potential from C to D won't be a potential drop. It'll be a potential rise through that resistor. So that means that it is the product of current 2, R1, and notice that positive sign there. And that positive sign is there because we are going opposite the direction of the assumed current. And if we're going opposite the direction of the assumed current, then that would mean that when we go from point C to point D, point C is at the lower potential, point D is at the higher potential. So that would be a potential gain. And again, this is based on our assumed direction for current. And as long as we stay consistent with these rules, we'll get the right answer for current. At worst, the sign of the current might be a negative sign. And if it's a negative sign, that just means the current is opposite the direction that we assumed, but the magnitude of the current will be the same. So now we can write the potential from C to D is equal to positive I2 R1. And remember, the resistance through resistor 1 is equal to 2R. So we could write this as 2I2R. And finally, in going from D back to A, we go across battery 2. So in going across battery 2, notice how we are going from the positive terminal to the negative terminal. Whenever you're going from a positive to a negative, you have to subtract the potential difference across that battery. So the potential difference from D to A is equal to minus the EMF of battery 2. And remember, battery 2 has twice the EMF of battery 1. Again, that minus sign is because we're going from the positive terminal of the battery to the negative terminal of the battery. So that means we have the potential from D back to A is equal to minus 2 times the EMF of the battery 1. And now let's look at Kirchoff's law for that entire loop. So the potential difference from A back to A, remember, is the potential difference from A to B plus the potential difference from B to C plus the potential difference from C to D plus the potential difference from D back to A. This is equal to the EMF of battery 1 minus 2 times the current through resistor 1, R, plus 2 times the current through resistor 2, R, minus the EMF of battery 2, and this all sums to 0 for this complete loop that we are moving in. So this is the information we gain from using the first loop. Notice in this problem we have two unknowns. We have the one unknown is the current through resistor 1, which we're trying to find anyway. The other unknown is the current through resistor 2, which we're trying to find anyway. So this is one equation, two unknowns. This means that we need another equation to find one of those unknowns. Where that other equation comes from will be from the second independent loop we have chosen.